Okay, still working through our bot manager. This is a little sidetrack. So I've been doing the robot operating system, or ROS courses, working through ROS1 at the moment and ROS2. Just finished ROS1 course. There's my certificate to prove it. And now what I want to do is understand a bit better is how ROS is used in the network. I'm going to be using distributed nodes in my for my robot, so have the different nodes running on different hardware and communicating with each other. And I'll feel better if I actually know what that looks like from the network point of view. So I'm going to pull out Wireshark, some of my network analysis tools, LupinPet, and then run some tests both with ROS1, both locally and distributed, to see what it looks like on the network. And then also with ROS2 to see what it looks like when it uses the DDS bus to communicate. So it should be interesting. This is a little sidetrack from most of our bot manager work, but I think it'll set me up to have a better feeling for how to set up nodes and things as I actually construct my robot. So here's the plan for the tests. So I'm just going to run through the same test script for ROS1, where I have the nodes on the same machine or where I have them distributed across different machines, and get the Wireshark network traces of what's happening. I'm going to use the same script. I'm going to try and leave 10 seconds between each of these steps so that hopefully I can pick up what's happening on the Wireshark trace. So the things I'm going to do is, first I'm going to start up the ROS master by calling ROS core. Wait 10 seconds, and then I'll do a ROS node list. Wait 10 seconds. Then I'll do a ROS run of this publisher, Robot News Radio Transmitter, which publishes a message on a topic. Wait 10 seconds. Then I'll do a ROS node list, and I should now see that node in the list. Wait 10 seconds. Then I'll do a ROS node info on that Robot News Radio transmitter, so I should get more info about that node. Wait 10 seconds. Then I'll do a ROS topic list, which will show me the topics being published. This Robot News Radio topic should be published, so after 10 seconds I'll do a ROS topic echo on Robot News Radio, so I should be able to see what this Robot News Radio transmitter publisher is publishing. Then I'll wait 10 seconds, then I'll run a subscriber node to that topic as well. So I'll do a ROS run of smartphone.py, which listens to the Robot News Radio topic for that publisher. So the network set up for this first test, everything's going to be running on this machine, Aspire-Ubuntu, and that's the IP address of that machine. ROS core will start up. It will run on port 11311, which is normal for a ROS master. I'm going to have Wireshark looking at all the local traffic, so it should see everything going on between the nodes and the master within that machine. I'm going to run the Robot News Radio transmitter, which publishes a topic, and then I'm going to run smartphone, which subscribes to a topic. So while all that's going on, I'll have Wireshark capturing all the traffic. Okay, we're all set for our tests. So you see here, this is Wireshark running on Aspire Ubuntu. I'm going to start it listening on the loopback interface, so it sees all the internal traffic on that machine. Over here I've got 5 tabs that are SSH'd into the Aspire Ubuntu machine. So first let's start up ROS core. So that's started. And wait 10 seconds, and the next command is a ROS node list. And I'll wait 10 seconds. Then next up, I'm going to run the Robot News Radio transmitter. So that's started. I'll just wait 10 seconds. go back, have a look at the ROS node list. And we'll just wait 10 seconds. I'm going to do an info on that that node. So that's all the information about the node, including what it publishes, Robot News Radio. So I'm going to do a ROS topic list. So we can see Robot News Radio has been published. Just wait another 10 seconds. And then I'll do the run a ROS topic echo now. So there you see it receiving the information in that topic being published. So I'm going to stop that. And I'll just wait for 10 seconds to expire, and then I'll write the smartphone Pi. So that's a node that's running as a subscriber on that same topic. So I'll start that now. And you see it's picking up the messages on that topic. Okay, let's have a look at the setup for the distributed network test for ROS1. So in this case, I've split the components for ROS across 2 machines. So the machine I was using last time, this Aspire Ubuntu 128, is now going to act as the ROS client. So it's going to run the nodes, but not the ROS master. And then over on this new machine 153, which is just called Ubuntu, it's going to run the ROS core, and then they'll be connected through the network. So a couple of things I had to do, which are changes in environmental variables, is for the ROS master, I actually used this export ROS IP and the IP address of the master. And by doing that, it doesn't use the host name, it uses the IP address when it's communicating to the node. So it just takes DNS out of the picture. Then on the client, to make sure it's using the ROS master on this other machine, I changed the export of the ROS master URI to point to 153, which is where the ROS master is now located, and also told it to use an IP address rather than the host name. Again, takes DNS out of the picture, so I don't have to worry about DNS doing anything weird here. So it's going to communicate to the ROS master with the actual IP address rather than the host name. Otherwise, I set up Wireshark on the ROS client. It won't see traffic that's just happening on the ROS master, but I don't think I need to see that. But it will see internal traffic between the nodes on the client, as well as traffic going out onto the network where it is talking to the ROS master. So that should tell me just about everything I want to know about what's talking to what. And let's try executing this and see what it looks like. Okay, let's try the distributed node test. We'll run through the script. I've got Wireshark all set up to run here. So let me start that up. I've got some filters in just so I don't get too much extraneous traffic. I'll still need to clean it up afterwards. So let's start this. And let's start the ROS core first. So that's running on 151. Sorry, 153. And now let's run through the scripts. So it's been about 10 seconds. So let's run the ROS core node, ROS node list on the distributed machine. Give it about 10 seconds. And I want to run this Robot News Radio transmitter, which publishes a topic. So I'll start that. So I'll just leave that running. So I'll do the ROS node list again. So now we see the robot news radio transmitter running. Let's give that 10 seconds to settle down. Let's do an info on that. So I can see it's running on 128. Give it another 10 seconds or so to run through. Let's do a ROS topic. So I can see Robot News Radio is the topic that's being transmitted by the publisher here. Let's subscribe to that through the ROS topic echo. So we see the messages there. I'm going to stop that. I'm just going to wait a little while for it to settle down. So I'm still seeing things talking to each other, so I might give this a little time to see if it actually stops publishing. That's interesting. Still keeps going. Let's start up another subscriber here. My Robot Tutorial Smartphone Pi. So you can see that's receiving the subscriptions. And I'm going to stop that. And I'm just going to wait 30 seconds or so to see whether the data transmitted to that node stops as well at some point. I'll be able to tell it's going to that node based on the port it's sending to. Still seeing a lot of 128 traffic going on. I wonder if I close this under actual window whether it makes a difference. Okay, I went through the traces, cleaned them up a bit, also noted down the more exact time of when each of the script actions occurred in the trace. So if you look at the relative time values in Wireshark, or I'm going to actually use LupinPet to look at them, this will sort of get you in the right area of the trace to analyze what's happening. So let's have a look. I'm going to go over to LupinPet. So this is a trace analyzer I wrote probably about 15 years ago, but I find it a good way to sort of summarize what's going on with conversations. Wireshark's a bit too detailed for things, so let's first have a look at our local execution where I've cleaned up the code a bit, and you can sort of see some of the times popping out here. So for example, at 13.8 seconds you start seeing things happening. 30 seconds is when the next script action occurred. Again, this is all happening on a on a ROS instance where everything's set up to happen locally, the nodes and the node master or ROS master are all running on the same machine. So you see it's all 127.0.0.1 to 127.0.1.0.1, at least the important things. So some of the things you can pick out on this view of what's happening. So this is looking at all the different port level conversations going on. So where there's a unique source and destination port combination, that throws it out as a set of activity when it started, when it stopped. So we can see, for example, at 13.85 is when I first did a ROS node list. It shows a little blip of network activity. So let's go over and look at the drill down on this, and again ignore some of this stuff in here. So I'll try and stay on the interesting stuff. So at start time 0, that's when I first fired up the ROS master. So all this is just stuff you see the ROS master doing. But let's go down to at 13.85. This is where I did the ROS node list command, and you can see here it's just sending a request going between let's just pull out the addresses here a bit, going between a port that represents the process that's running the ROS node list command, so 45858, and it knows based on the environment setting that the ROS master is local on port 11311, which is standard for ROS1 ROS master. And we can see what the actual conversation was. So it's going out there saying, hey, I want to get the system state for ROS nodes is the request when you look at the API, and here comes back the information. So there's a bunch of information here, but if we can pull off one thing, we see ROS out is among the values being returned, and that's what it shows on the console when you do it. So the next thing I did was to fire up the publisher, the Robot News radio transmitter. That happened at 30th second mark. So you can see it started having its conversation this time. The process that represents the ROS radio transmitter is again talking to the ROS master. Interesting point here is that this last command here, so you can see here where the publisher is getting registered, and the name of the topic is shown here as Robot News Radio. So that's how it sort of communicates that it's publishing a certain topic. Again, it's going between the instance that represents, or the process that represents the publisher, the actual program that's the node that's publishing, and the ROS master. And next thing to notice in here is we can actually see the 117185. Okay, now that's publishing now. So I'm going to dive down here. Next command I'm going to look at is where we've got the smartphone subscribing to the ROS radio transmitter, and that starts at 17164. So here we see the same sequence of registering of the smartphone node, and the last thing it does is says it's going to subscribe to this topic, Robot News Radio, and then we actually see the the publisher and the subscriber tied together. So this is the actual publishing node. 42146 is the port it's using, and then the subscriber node, which is the smartphone node, is opened up port 38309 to receive, sorry, 33728 to receive the things being sent from the ROS publisher. And there we see in the content of that conversation the actual content being sent over the topic. So generally when it's in local mode, you see it talking to the ROS master for ROS commands, and when publishers and subscribers first start up to negotiate, identifying them, what they want to do, information about topics and things like that. But the actual publishing and subscription, when there's an actual publisher and a subscriber active, the data flows between the actual nodes without involving the ROS master. So let's compare this to what happens when I distribute the ROS master on a separate machine from the nodes. Okay, now we have a look at the distributed version of the tests. So these are the times for the different operations down here, and I'll try and show those on the analysis. And we'll switch over to the distributed execution, and I've cleaned up the traces here as well, and I'll try and provide links to the 2 PCAP files or 3 PCAP files once I get the ROS2 stuff in here, so that people can download and use Wireshark to view them, or bring down LupinPet, which is free to use as well. Okay, so let's have a look at the conversations here for that distributed execution, and we can sort of see where things are happening here. I've got one sort of orphan packet at time 0, just to keep all the times working for reflecting relative times. And we can see things like at when the first ROS master was started up, we're not seeing any of that traffic because that's all happening out on the .128 machine. I don't have Wireshark running over there, but don't think we really need to see the internal traffic out on that machine. But the rest of them, we see all the traffic. So for example, doing the ROS node list from the 153 machine, sorry, the 128 machine, talking to the ROS master on the 153, we see the conversation there, and we can see the sort of the blips in network activity as these different things happen. So let's have a deeper dive into the turn details. And so first one to have a look at is 13.8. Sorry. At the 26 second mark. So 26 second mark is when we do a ROS node list. So going from the 128 client machine and the process that reflects the ROS node list command, going up to the ROS master on the 153 machine, and we see the same sort of thing where it goes out and does a get system state and returns information about what nodes are running, including ROS out. We see here that the communication is communicating the IP addresses, which is what we want in this case, just to take DNS out of the picture. But you could run this with the ROS IP not set and get all the host names, as long as you have DNS that keeps in sync with all the nodes and the ROS master. Let's have a look at where we fire up the topic publisher at, so the robot tutorials, robot news radio transmitter. That's happened at 45 second mark. So we're see the same sort of thing happening, except it's between the two machines, 128 talking to 153. And if we run down this list, we see the last thing that happens is it advertises that it's publishing on topic robot news radio. Next interesting things that happen, let's go down and have a look at the ROS topic echo. So that's happening at the 149 mark. So it runs through the comments on that. Then the actual echo transactions starts. And you see here it's receiving the information about what's happening on that topic. So it's getting the strings from the topic. But the interesting thing here is it runs right through to almost the end point of the trace with this. Even though I stopped the echo after about 10 seconds, it continued to run. I don't know why that's happening. There may be an actual bug in ROS1. It seemed to happen with the ROS echo, but didn't seem to happen with the ROS when I actually run the smartphone subscription service. So maybe it's not processing the end of the ROS topic echo command the way it should. Now let's have a look at the ROS topic smartphone subscriber running. So that starts at 214. So it looks like it's 216 on here. It's showing the time, and it's going through registering the subscription as you'd expect. And then when the actual subscription is active, we can actually see the content of this, the publisher, which is running on 128. And I think this port represents the node 52404, and it's talking to this port on 128. So it looks like it's talking directly between the publisher and the subscriber nodes. So after it's done its setup using the ROS master, it looks like it just falls back and talks directly sort of inter-process communication between the two nodes, which is good. And we can see it happening here. The other interesting thing in here is this one actually stopped. So when I stopped the subscriber node at 223 seconds or 224 seconds, it seemed to actually stop the subscription activity. So it worked differently from this one up here. So this again, the ROS topic echo seems to not stop the subscription the way the proper subscribers do. So maybe a bug in there, but the rest of it worked the way I kind of expected. Was the remote client will talk to the ROS master while it's setting up connections. Once publishers and subscribers are registered with the ROS master, then communication between the two goes directly on the same machine. Okay, for the ROS2 tests, so these tests I only did in distributed mode. Wasn't much point looking at them running locally. So I've got two machines. I've got this Aspire Ubuntu running on 128, and then I've got an Ubuntu it's running on a Raspberry Pi on 153. You'll also notice in the YouTube description I put down the steps I used to set up Ubuntu and ROS2 on my Raspberry Pi 4. I had 2 gig of memory. Took me a while to get it right. I made some mistakes along the way, so the instructions are a good way of just seeing how to do it for Raspberry Pis. So the environment here looks different from ROS1, has no ROS master, and ROS2 uses multicast across the network to communicate between nodes and the instructions. So really on each machine I'm just using Wireshark to look at the loopback and the traffic going out on the network. other things. Each of these machines also had wireless wireless networks as well. So you'll see in the traces later on, I filtered out the traffic that was going out on the wireless interfaces of these, just because the way multicast and ROS2 works, it'll use all the networks available and send out all the DDS info on all the networks that are available. Otherwise, I used 2 nodes that came with ROS2 in their demos packages. So one's called Talker, which publishes a topic called Chatter, which is really just a hello world type thing. And then this listener node, which just is a subscriber and will listen to the chatter messages. So that's how I exercised it. Then I used ROS2 commands to do same as I did with ROS1. Did a node list and a list of topics and echo on the topics. Here's the script I use for the ROS2 tests. Fairly much follows the same tasks as for my ROS1 tests. So let's have a look at them being executed, and then we can look at the details of the data that was captured. Okay, you're going to capture the ROS2 script. To do this, I've got a bunch of terminals open and Wireshark open on each of the 2 machines which will host the nodes. Just like before, I'll run Wireshark with some basic filters in there just so I don't get too much traffic, and then I'll still have to clean up after the fact. So let's start and see how we go. So let's start both Wiresharks. Okay, we're capturing on both machines. So let's start on the Aspire Ubuntu machine, the 128, and I'll just do a ROS2 node list. And not seeing anything. I haven't got anything running. There's no master running with ROS2, so nothing's really out there. So let's try running a publisher. ROS2 has a demo one available. So ROS2 run. Our publisher's running on 128. Now let's try a node list on the same machine. So now we see the talker. I'm going to go over to 153, the Ubuntu machine, and do the same thing, ROS2 node list, and see if we can find the node that's running on the other machine. So that's good. It can see the talker. Let's try getting some info on that one. ROS2 So that works successfully, and now let's try running a listener on this second host. Let's have a run in there. So that's subscribing to the messages sent out by the talker. It's running on a different machine. So that's all working successfully. Let me stop the subscriber. I'll just give it 10 seconds. I'm going to try, same as I did for ROS1, do a echo on the topic. So ROS2. And chatter is the topic. I'll stop that. I'll go back and stop my publisher, the talker. Let's run the traces for a little bit longer just to see if there's a point at which everything stops talking to each other. So I'll stop the traces and then we can have a look at them. Okay, let's have a look at the network captures from the ROS2 test. So I captured on both hosts, so the Aspire and the Ubuntu host, so it's the end of the IP address for each of those. I went through the traces, I cleaned them up, so I actually found when I first looked at them that the majority of the traffic is this RTPS and IGMP are the ones of interest, so filtered down to those and some extra protocols that DDS uses. And also on each of the hosts I had both a Ethernet and a wireless LAN interfaces, multicasting out of both the interfaces. I didn't want to see the wireless LAN side of things, so I also filtered out any traffic coming from the wireless LANs on Aspire or the Ubuntu hosts, and then finally I just left in the first frame in the trace just so that all the timings stay consistent even as I clean them up. So these are the activities and what host I did them on. I did one actual extra activity at the end called Stop Talker, where I just stopped this talker up here, so the publisher node on 128 at this point, just to see what happens when everything becomes inactive. I saw there's some resources out on the net too, including this fine-tuning PDF. So how you can fine-tune what amount of the network it's going to broadcast to with the multicast, how you can restrict the nodes that can see a particular set of multicast instructions. So that presentation is quite useful. I also found some interesting settings. So you can export the ROS domain ID. By default it's set to 0, but if you want to have multiple ROS domains running on the same subnet, then by setting this domain ID in an export or an environmental variable, you can restrict the node participants just to that domain even though they're sharing the same network. And this address here is the ROS2 multicast address, so you'll see that in the traces as I go through. So let's have a look at the traces. I'll also make these trace files available for anyone who wants to look at it through Wireshark or LupinPet later on as well. So let's bring up the Aspire side trace in LupinPet and just look at the main conversations here, and you see some of the main timings drop out at this 23-second point. You see it starts responding to a ROS2 node list instruction. But let's look at the turn details. So there's some interesting stuff in here. And again, the decodes on LupinPet are really just about changes in direction of the traffic. Don't really decode to a great extent, but we can pick some things out of here and then drill down in Wireshark to see some of the details. So you see the majority of the traffic is this RTPS protocol, and we can see sort of the key points and when things happen. So 23-second points when I first did the ROS2 node list instruction. You can see it start talking to things like the multicast address here. Let's actually have a look at that in Wireshark just to compare it. So open up that same trace and let's go down to around the 23-second mark when things started. So you can see IGMP traffic starting as well. So this is where it starts advertising that there's going to be a multicast address that some groups want to join. So that's probably the main discovery mechanism. After that, it sends RTPS traffic to the various hosts that are involved in the multicast, and the majority of the negotiation and sending data is done through RTPS. One interesting thing I saw, I think it's at 202. Let's go zap down here, 202. Actually, let's go back to LupinPet, go down to the 202, 903. So this series of communication between the Aspire node here and port 60448 and the Ubuntu node here on 1353 on port 7415, that seems to have all the actual communication of the chatted topic. There's various setup messages here that tell you the truth, I can't really understand, but you can look into the RTPS protocol to see what's actually happening. But I'm guessing that's a bunch of negotiation about what topics are to be exchanged and who's doing it. But let's have a look here. So we can see the actual published data being transferred across the network here from 128 to 153. And I'm going to get a display filter of this set of traffic to use in our Wireshark. So this sort of breaks down that whole conversation. You see the RTPS activity in detail here, and this Wireshark does a nice breakdown of the protocol. So one thing you'll notice in here is domain ID. So at the moment it's 0. That's the default for ROS2, but you can set a domain ID to be something different if you have multiple ROS collections of nodes running on the same network to separate them. So it goes through, does negotiations, and then you start seeing down here where on these heartbeat messages where the actual hello world has been transferred. And again, it's going between, so all these are going to be between the same ports, which was interesting. So 60448 on the sender side and 7415. So it started at 204, but you also see I have a bunch of things happening here at 4249. So this is where I'd actually close down the listener and was now running a ROS2 topic echo chatter, so a different way of subscribing to the the data. But the interesting thing is it's going to the same destination port in both cases, so it makes me think there's some sort of intermediate process that runs on these ROS2 hosts that all the data is going to, and then it's redirecting the traffic to the particular node or command, ROS2 command that needs to get the traffic. So that was kind of interesting. I was expecting to go directly to a different destination port for different nodes running on the machine, but it looks like that traffic management is probably done down in the DDS stuff that's running on the machine. So that's about as far as I was going to go with this. So the interesting thing is, compared to ROS1, it's quite a nice protocol, kind of a lot more complicated, especially because things aren't so much in plain text with RTPS, so you really need the decode to see what's happening. Makes it a bit more compact. It's nice that it's using the built-in multicast capabilities of IP networking. The other note here is this is running under UDP as the overall protocol. So again, sessionless protocols, they should be a lot more efficient. A lot of the stuff is compressed, or which is good as far as content other than this actual string. Should be a lot more efficient, and it's nice not having to run a particular ROS master like you do in ROS1 to have all this thing working. It just, once set up, it all worked pretty nicely out of the box across the network. So that's about it for how far I'm going with the network analysis, but this tells me the details of what's happening, and then I think as I work on the actual robot code, if I run into problems, then I'll have these traces of sort of the basic activity and how to get these traces to use later on to do a deeper dive if I'm having any problems with communication or what's happening on the nodes.